Thank you very much, Philip. Thank you very much, Alina and Mike, for inviting me. It's an honor to speak in the number 3 web seminar. So talk number 250. It's really great. Thanks very much for the time and the energy that you have invested to keep this seminar running. I think it's a great service to the community. Thanks very much. Okay. Much of what I present today comes from joint work with Shabnam Akhtari and Jeffrey Vaaler, and it is motivated by a paper of Wolfgang Ruppert from 1998, in which he proposed two precise questions regarding the smallest height of a generator of a number field. One of these two questions is solved completely by now, but the other one has morphed into a conjecture. Some people have started it to call it Ruppert's conjecture about 3-4 years ago, and much of my talk is going to be about this conjecture. Then at the end of the talk, I will also mention a connection to upper bounds for the l-torsion part of number fields, which was highlighted or found by Ellenberg and Venkatesh in 2007, and inspired by that, Jordan Ellenberg has proposed a question, and I will address this question at the end of the talk. Okay, so much about the plan of this talk. Oops. So here's a first variant of the question that leads to Ruppert's conjecture. It's as follows. So you're given a fundamental discriminant d, and the question is, can you find a quadratic integral polynomial whose discriminant is equal to d, and such that its naive height is bounded from above by some absolute factor times the square root of the modulus of the discriminant? Here, the naive height is of course just the coefficient max norm of the coefficient vector of the polynomial. And since the field q square root d is monogenic, you certainly can find a polynomial with the discriminant condition, but it's not so clear that you can find one that also satisfies the height condition. There's two cases to consider. If d is positive, then the question is trivial. You can even take a monic polynomial, then you take b to be essentially the square root of d, make sure b has the same parity as d, and then c is b squared minus d over 4, and you see that all the properties are satisfied. So it is a polynomial of sufficiently small height. Now, if d is negative, then the task is to add squares to the modulus of d in order to produce a number which is a product of two numbers, both of the size square root of d. And this is not so easy, but Ruppert observed that even in this case, the answer to the question is yes, such a polynomial does exist. And what Ruppert found was that it is a simple consequence of a beautiful equidistribution result of Bill-Duke. So here's what is this equidistribution result of Duke? Well, consider the upper half plane in the complex plane. Consider the modular group PSL2Z acting on the upper half plane by Möbius transformation, and let F be the standard fundamental domain for this action. There is a measure, hyperbolic measure, on the upper half plane, and you normalize it such that the total measure of F becomes 1. Now let D be a negative fundamental discriminant, then you can associate to D the set of its Heegner points, which are simply the roots in F of a polynomial, quadratic integral polynomial with discriminant equal to D. And of course, their number is just the class number of the field q square root of D. And so if D tends to minus infinity, you get more of these elements. And the question is, how do they distribute in F? And the answer is, well, if you pick essentially arbitrary subset omega of F, well, it has to satisfy some niceness conditions, but they're fairly generic. and you look at the number of Heegner points inside the set omega and divide by the total number of Heegner points, then this will tend to the measure of omega as d tends to minus infinity. And you even have a power-saving error term. Okay, so that's the equidistribution result of Duke. And so how does that imply Ruppert's theorem? Well, you simply got to pick a nice set omega, so one to which the equidistribution result applies, which is somewhat close to the point, to the complex point I. So every point in omega is not far from I. And of course, you want omega to have positive measure. And then you know from Duke's equidistribution result, from a certain point on, so if d is smaller than d naught for a certain d naught, you are guaranteed to have a Heegner point Zd inside omega. And then it's simply using the fact that Zd must be close to the point, complex point I, you immediately get the required conditions on A, B, and C. And so you have the existence of your polynomial f. All right.
There's a question in the chat. So in the definition of omega d, are A, B, and C, the integers, assumed to be co-prime?
No. Let's see. No, we have d to be a fundamental discriminant. So d is a fundamental discriminant, so it follows. So it follows from this assumption. D is always assumed to be a fundamental discriminant. Okay, all right. So now the question, okay, how do we take it from there? What's the obvious, well, what are possible generalizations of these questions? Well, of course, one thing you can do is you can think of the previous question as a question on a binary quadratic form and look at associated at degree d forms of binary degree d forms of higher degree. And you could fix an invariant under the action of the modular group, for instance, discriminant, or even a complete set of invariants under this action, and then look for the smallest height of a form with these invariants. And that leads into the direction of reduction theory, a well-studied topic. But we're not going to go down this way. We are doing something rather different. Instead, we're looking at a variant of the previous question in which we do not fix the discriminant. More precisely, we fix the discriminant only up to a square, or what amounts to the same. We only fix the field that is generated by one of the roots of the polynomial f. Okay, and that was exactly the question Ruppert had in mind. Okay, and so this led Ruppert to the following question. As I said, Ruppert never formulated as a conjecture, but a few years ago, it kind of some people started to call this Ruppert's conjecture. And so Ruppert's original question was, if you're given a number field k, and throughout this talk, d will always denote the degree of the number field k, the question is, does there exist a constant CD such that there exists a generator alpha of the field k whose height of the minimal polynomial of alpha is at most CD times the square root of the modulus of the discriminant of k. Okay? So Ruppert's theorem tells us that the answer to this question is certainly yes if d is 2. So Ruppert proved it for d equals 2. And it's not so clear whether the 1/2 is the right exponent in general. But it turned out that this is probably the right exponent. But before we go on, let me introduce the Weyl height. Turns out a slightly better height to use, which is more natural and leads to better constants in the sequel, is the Weyl height, which is defined as on this slide. So it's a product taken over all places of the field K. For each place, you choose an absolute value that extends either the standard absolute Archimedean absolute value on Q or one of the standard periodic absolute values on Q. And dV in the exponent denotes the local degree at the place V. So in this definition, so as you have the global degree d in the denominator of the exponent, the entire definition is independent of the particular field K that you choose that contains alpha. And more importantly, the height, the Weyl height, or more precisely, the Dth power of the Weyl height is comparable to the naive height that we were considering before, where the involved constants depend only on B. Okay, so now it's going to be quite handy to introduce an invariant delta of K. This is going to be the most important invariant of this talk. And it's simply the smallest height of the smallest absolute Weyl height, to be more precise, of an element that generates the field K over Q. And we're going to write dk for the modulus of the discriminant of the field. And with these quantities at hand, we can reformulate Ruppert's conjecture. It's simply the claim that the delta invariant is bounded from above by dk to the 1 over 2d up to some factor depending only on t. Okay, so I've already mentioned it's not so clear whether this exponent 1 over 2d here is the right one. So what kind of lower bounds does one have for the smallest height of a generator? There's a classical result of Silverman, which tells us that delta k is always at least essentially dk to the 1 over 2d times d minus 1. And you see for d equals 2, this exponent coincides with the previous exponent from Ruppert's conjecture. And therefore, in the same paper, probably motivated by this observation, Ruppert has also asked a very strong version of the other question, namely, is it in fact true that the delta invariant is almost always bounded from above by dk to the 1 over 2d times d minus 1? And this is asking too much. So this question has been completely solved. The answer is no, that's not true unless d equals 2. And it comes from work of Vaaler, myself, Dubitskas, and Patil. Okay, but more is to be said on lower bounds for the delta invariant. It's quite easy to construct fields that have a large delta invariant. If you have a divisor n of d strictly bigger than 1, you can easily produce infinitely many fields k whose delta invariant is essentially, so is bounded from above as well as from below by dk to the 1 over 2d times n minus 1. So in particular, if d is even, you can choose n equals 2 and you get a lower bound dk to the 1 over 2d. So if Ruppert's conjecture is true, then the exponent is certainly sharp when d is even. Okay. There's also a kind of a trivial bound that one always has, and this is even for an integral generator. So in any number field, one has an integral generator whose height is at most the root discriminant of the field. Okay. So if we want to make progress on Ruppert's conjecture, we got to have a way to produce generators of a number field. And here's a very simple observation, but that turns out to be quite useful. We're going to assume for this that K has at least 2 Archimedean places. We've already seen that the imaginary quadratic case is already settled by Ruppert's theorem. So let W be an arbitrary place of the field K, and we associate to W the subset of K of elements whose absolute value is bounded from above by 1, with possible exception at the place W. And if the absolute value comes from an Archimedean place, then the inequality is strict. Okay, and here is this very simple but useful lemma. If the local degree of your place W is 1, then any non-zero element in OW is a generator. And to see why, let's just denote by lowercase k the field generated by alpha, and let U be the restriction of the place W to lowercase k, then we first observe that U extends to capital K only in one way. Because if it had two extensions, W prime and W, then clearly, because of this identity, or the absolute value of alpha at W and at alpha and at W prime is equal, it follows that all absolute values of alpha are bounded from above by 1. But at least one of them must be strictly smaller one, because we have at least two Archimedean places. So this gives you the right-hand side. This product is strictly smaller 1, but by the product formula, it is equal to 1. So a contradiction, and hence W is really the only extension of U to capital K. So this means by the fundamental formula that the relative degree, so in other words, the index of lowercase k in capital Ks, is precisely the local degree, the relative local degree of k, lowercase ku in uppercase kw. And since this is a divisor of dw, the claim follows. So indeed, lowercase k equals capital K. Okay, so we can apply that observation very easily in the situation where we have an Archimedean, real embedding. So when W is an Archimedean place of local degree 1. So we consider OK as a lattice embedded into Euclidean space of dimension d. And we introduce this constant ck, which is essentially just dk to the 1 over 2d. So this is the upper bound in Ruppert's conjecture, up to a factor that is at most 1. And a straightforward application of Minkowski's convex body theorem gives us the existence of a non-zero integral element in OW, whose absolute value at the place W is at most, well, 1 plus epsilon times ck to the d. But Northcote theorem, of course, allows you to drop that 1 plus epsilon, because there's only finitely many alphas that really show up. And so what you get is that not only do you find a generator of height at most ck, you find even an integral generator of height at most ck. By the way, so this observation that such an alpha exists is true even if the place has a local degree 2. It's just that in this case, we don't know that the alpha is a generator. So what we learned from that, Ruppert's conjecture is nearly trivially true when K has a real embedding. So we can now consider totally complex number fields. And what we have already learned on the first slide is that in this case, at least for imaginary quadratic fields, the integral generators are all ways too big. So their size is at least of order square of the bound predicted by Ruppert. And so the question is that a general phenomenon? What happens for higher degree totally complex number fields? Are there integral generators always big in some sense? And the answer is yes. Whenever you have a totally complex number field, the smallest integral generator is significantly bigger than what you get from just applying Silverman's bound. So you see Silverman's bound had the exponent on the discriminant 1 over 2d times d minus 1. Here you have d minus 3 half. That's a little bit, but significantly bigger. And the proof of that inequality has nothing to do with number theory. It just comes from looking at monic complex polynomials whose roots outside the unit circle come in pairs of equal modulus. And that's already enough in order to get the inequality for the Vaaler measure as stated on the slide. And in this inequality, the exponent 2d minus 3 on the Vaaler measure is actually sharp. You cannot improve on that. And this improves on a classical inequality of Vaaler from 1964 in the special case where f is monic and you have this symmetry on the roots outside the unit circle, and if the discriminant is big in comparison to the degree, because the dependence on the degree is in our inequality much worse than in Mahler's original inequality. Anyhow, so what we see is, unfortunately, this exponent 1 over 2d times d minus 3/2 is too small in order to be in conflict with Ruppert's conjecture in the case d is bigger than 2. So that doesn't tell us much, but there is another way to generalize the observation of the imaginary quadratic case. Namely, you can consider only an infinite subfamily of CM fields. And for these guys, it's very easy to prove, no matter what their degree is, that the smallest integral generator is in fact pretty much as large as the trivial upper bound you have. So they really have only very big generators that are integral. And of course, this bound is contradicting Ruppert's bound. So if you restrict Ruppert's conjecture to algebraic integers, then it is definitely false when d is even. Okay. So now that means we got to consider also non-Archimedean places. So our strategy, of course, also applies in this setting. Recall we had this set OW, and if W is now a non-Archimedean place of local degree 1, well, it comes with a prime ideal frag P and a rational prime P. And we're now going to apply Minkowski's convex body theorem to the fractional ideal frag P to the minus n, where n is chosen sufficiently large in order to get the Minkowski's convex body theorem applicable. Of course, this n enters as the determinant of the lattice, which you see here when you embed the lattice via the standard Minkowski embedding. So what this means is, as soon as p to the n is bigger than ck to the d, you can apply Minkowski's convex body theorem. It provides you a non-zero alpha in OW, which then, of course, is a generator. And the contribution of the place W is at most p to the n, to the height. Well, to the relative height. So what we learn from that is, if there is a prime p that splits completely in the number field k, and there is a positive integer n, such that p to the n is strictly bigger than ck to the d, but bounded from above up to some constant depending on the d by dk to the 1/2, then Ruppert's conjecture holds for k. Okay, so we're in the usual business of trying to prove the existence of a prime, say splitting prime here, of the right size. And what we need is certainly true if GRH holds for the dedecant zeta function of the normal closure of k. But of course, we would like to have an unconditional result. And one way, in one case, we can prove such a result is when k over q is abelian of sufficiently large degree. In this case, a sufficient condition for splitting can be formulated as a congruence condition modulo the conductor f. And the conductor f is well controlled in terms of the discriminant. And Linux theorem gives us a prime in the residue class 1 mod conductor and of size at most f to some absolute L. And thanks to the work of Heath Brown and Xilouris, one can take L to be 5. Now, the important thing here is Linux proof is quite robust. And it allows you not only to produce a small splitting prime, it also allows you to produce a splitting prime in the right interval, the right short interval. And therefore, we get exactly what we need, but we need a condition on the degree because the condition, the bound on the conductor and the bound on the splitting prime, if you combine those, then they translate to D has to be at least 4L. So this means Ruppert's conjecture holds for all abelian extensions of sufficiently large degree. Okay, so what can we do if we have a small splitting prime, but if the prime is too small? Well, of course, you can look at the ideal or the lattice frag p to the minus n, and you just choose n sufficiently big in order to reduce the determinant of the lattice appropriately. And without any further knowledge, immediately what you get is an upper bound for the delta invariant of the form ck times p to the 1 over d. There has been a lot of work in the recent years regarding upper bounds for the least prime p that splits in number fields k of certain families. And some of these results give new upper bounds. So I mentioned just one quick result here. Pollack has shown that the least splitting prime in an abelian extension is at most of order dk to the 1/4. And plugging this in gives you a non-trivial upper bound for the delta invariant with an exponent halfway between the trivial exponent 1 over d and the conjectured bound exponent 1 over 2d. And this holds for every abelian k. All right, so, but what can we do if we are unable to prove the existence of any suitable prime at all? Well, we still can squeeze quite a bit of extra information from the Archimedean case. So here's a recent result of Shabnam, Akhtari, Jeff Vaaler, and myself. If K is a totally complex number field and F is its maximal totally real subfield, then the smallest integral generator is at most Ck times the height of mu, where mu is any algebraic integer in K that is not totally real. So for instance, if you have a root of unity in K different from plus minus 1, then the delta invariant of OK is at most Ck. There's an additional observation. If the delta invariant happens to be, for OK, happens to be bigger than Ck, then K over F is necessarily a Galois extension. And this additional structural result implies in particular that there must be a subfield of capital K of index 2. If you consider K to be embedded into C, then you can look at the complex conjugation. This must be an automorphism of K fixing F, because K over F is Galois. And if you look at the fixed field of the group generated by the complex conjugation, you get a subfield that has index 2 and sits in R. And since K itself does not sit in R, it must be exactly the intersection of K with R. Okay. So a few words on the proof. We consider only the special case where K has a non-trivial root of unity. So let's first prove that the delta invariant is at most Ck in this case. What we're going to do is, just as in the case where we had an Archimedean place of local degree 1, we pick an arbitrary Archimedean place, and we can construct a non-zero element alpha in OW, whose height is at most Ck, as we have seen before. Now, we don't know that this alpha is a generator because the local degree is not 1, but it could be, and in this case, we are of course done. If it isn't, then what we have already learned, then necessarily the index of this field, lowercase k, in capital K, is precisely the index of the completion of lowercase k in the completion of capital case K, and hence must be the degree of C over R. Okay. Now, what we do is we simply replace alpha by mu times alpha. Of course, mu times alpha still lies in OW because we haven't changed any of the absolute values. And for the same reason, the height hasn't changed either. But of course, now we are lifting Ku to C. It's no longer possible that Ku is still R, and that produces the conclusion that we now have a generator. So mu alpha is a generator. Okay, and essentially the same, well, a refined version of this idea proves you the first part of the On the second part, if the delta invariant is large, bigger than CK, then it follows that K over F is Galois. The first step is pretty much the same thing. Now, for every Archimedean place W, you construct a non-zero alpha W in OW, whose height is at most CK, and it gives you this field lowercase k. And we already know from the hypothesis none of these elements alpha can be generators. So therefore, as in the previous part of the proof, we conclude that the completion of these lowercase k's are just R. And in turn, the index of lowercase k and capital K's is just 2. And this means, in particular, that if you embed lowercase k w with the corresponding embedding sigma w, you do lie on the one hand in R, but of course you also lie in the embedding of capital K's k. And since the index of lowercase k and capital K's k is 2, you really have equality here. Okay, that has an immediate consequence, namely that if you intersect over all these fields lowercase k, then you do not only get a totally real field, but you get the maximal totally real subfield of k. And since each of these extensions, capital K's over lowercase k, are quadratic extension, they are all Galois, and hence by a general result from Galois theory, the extension k over the intersection of all these lowercase k's is also a Galois extension. Okay, so that's essentially the proof of that theorem. So I'd like now to move on and to connect small generators with upper bounds for class group. We don't see the connection here, but we shall learn about the connection in a few minutes. And so a bit background first. Let L be a prime number. We are looking at the l-torsion subgroup of the class group of K. And there is a famous conjecture due to Brummer and Silverman from 1996, which is called the l-torsion conjecture. And it tells us if we fix L and we fix the degree D and let K run through over the set of all fields of degree D, then the l-torsion part should grow more slowly than any positive power of the discriminant. This is a very deep conjecture that is connected to various other conjectures, such as Mollis conjecture or the multiplicity conjecture. And if you would like to learn more about this, I would like to refer you to the 2022 ICM Proceedings article by Lillian Pierce, which gives a lot of interesting information on this conjecture. There's one case where this conjecture is known, and this is for D equals L equals 2. In this case, it follows from genus theory from Gauss, which gives you that the rank of the two torsion part is given, the two rank of the two torsion part is given by the number of different prime divisors of dk minus 1. Okay, so a trivial bound that you have on the l-torsion part, of course, is just bounding the thing by the whole class group. And result of Landau gives us an upper bound for this whole class group as dk to the 1/2 plus epsilon. And the goal is essentially to improve this bound here for the l-torsion part. In particular, to try to improve this exponent 1/2. There are very few instances where this has been achieved, and usually the improvements are quite small. So here's, I believe, a complete list of the results that have been achieved so far in this direction. The first breakthrough was made by Pierce and Helfgott and Venkatesh in the year 2005-2006 for 3 torsion in quadratic fields with different ideas. And then another breakthrough was achieved by Ellenberg and Venkatesh in 2007, where they introduced a new method, a new tool, which is very influential, very powerful, and has many, many applications. This led also to a very substantial improvement for three-torsion in quadratic fields. A further breakthrough was achieved just a few days ago by Stephanie Chan and Peter Koymans. They were able to further improve this improvement 1/6 by 0.18 in the case of three-torsion for quadratic fields. The method of Ellenberg and Venkatesh also gives improvements to the exponent 1/2 for three-torsion in cubic and quartic fields. And another breakthrough was obtained by Bhargava, Shankar, Taniguchi, Thorne, Zimmerman, and Zhao in 2020. They are able to improve the exponent for two torsion for any degree, okay? And for 3 and 4, degrees 3 and 4, they get, in fact, very, very good improvements that have various other interesting consequences. I also would like to mention that recent work of Lemke, Oliver, and Saman appeared on the archive this year, gives an improvement on the trivial bound that we have seen for all D and L. They don't improve on the exponent 1/2, but they are able to remove the plus epsilon. In fact, they'll even get an additional logarithmic improvement. There are further results when you allow yourself to consider special families of fields. For instance, if you restrict the Galois group of the closure of the field, and there is an important work or two important works of Wang and also of Wang and Klüners, and there's also a preprint of Heath Brown. Okay, so what's the connection to the delta invariant or to small generators? This comes from a lemma of Ellenberg and Venkatesh from 2007 that I've already mentioned on the previous slide. And very roughly, it tells us that if there are many prime ideals of unramified and degree 1 of small norm, then we can improve the trivial bound by a negative power of the delta invariant. So more precisely, if you have d to the d over L minus, say, epsilon half prime ideals of norm at most d to the d over L, then you can improve by delta to the minus d over L. And if you plug in Silverman's bound, lower bound for the delta invariant, then you get this exponent 1/2L d minus 1. So you get this 1/6 in the case of quadratic fields and L equals 3. Of course, an obvious question is whether the bound of Silverman could be improved, but unfortunately, that's not the case, not in general. There are cases where you can improve on the bound a lot, as we have already seen. Sometimes the delta invariant is just dk to the 1/2d, in which case you get a much better saving here, of course. But in general, that's not possible. I've already mentioned under GRH, the hypothesis is guaranteed, but in general, it's a real pain to prove that the hypothesis can be assumed. And the proof idea, very roughly, in order to prove an upper bound on this l-torsion part, they consider the quotient, when quotienting out by the l-torsion part. And if you assume that this quotient is small, then you can cook up a generator of the field K, whose height, because of this upper bounds on the norm of the prime ideals, so whose height is strictly below the delta invariant, and that's obviously a contradiction, and so this quotient cannot be too small. So that's roughly the idea of the proof. Okay, so shortly after this paper of Ellenberg and Venkatesh, Ellenberg published a little note which did not get much attention. I believe it has only 4 citations, called Points of Low Height on P1 over number fields and Bounds for Torsion in Class Group. And so he writes, the aim of this note is to make the observation that the bounds of 3 could be improved if one had good bounds on the number of principal ideals of height at most x. We are led to precise questions about the distribution of points of low height on P1, which do not seem to have been well investigated either theoretically or experimentally. And Jordan told me that this note was inspired by numerical computations of his very first undergraduate research assistant, Daniel Lecone, who is now a very successful astrophysicist. So what's this observation that Ellenberg had? Well, in the proof of the key lemma, what really happens is one introduces, well, essentially, the idea is one can consider a prime counting function, n prime, of x, which simply counts the number of generators of k of height strictly below x to the 1 over d. And then what the proof really gives is, as long as x is such that you have at least x to the 1 over l prime ideals of norm below x to the 1 over l and degree 1, then you have an upper bound on the l-torsion part where you save x to the minus 1 over l times 1 plus n prime of x. So the idea is, of course, if x is bigger, well, then you save in the first part, but you might lose in, well, you probably lose in the second part. So what is the optimal value to choose in order to optimize your gain? And so you introduce this function or this quantity MLK, which is just the infimum of this possible improvement. And then this is for a fixed k. And then you look, well, what's the worst possible situation as k runs over all degree d fields? That gives you your FLD. And then, assuming that you have sufficiently many prime ideals, you get an upper bound with discriminant with exponent 1/2 minus FLD. Okay. And of course, now the question is obvious. So here it is. At present, it is not at all clear how to bound MK or FLD. As far as we know, it might be possible for M prime to start growing quite quickly once it becomes non-zero. In this case, we would have FLD equals 1 over 2LD minus 1, and no improvement would be made. It would be very interesting to understand more fully the situation for cubic fields. I noticed this paper several years ago, and I found the question quite interesting, and I thought about it, and well, because of the application, but also because I think I found it an interesting problem to estimate the growth of n prime. And turns out that unfortunately, FLD is not bigger than 1 over 2 LD minus 1. It's exactly 1 over 2 LD minus 1. At least if L is bigger equals d half, okay, which certainly deals or covers all the cubic case. All right, so it looks as if a direct implementation of the proposed strategy gives no improvement to the key lemma. And we already know FLD is at least 1 over 2 LD minus 1, so we only got to prove that it's at most 1 over 2 LD minus 1. So how is that done? So FLD was defined in terms of this function of this infimum MK or MLK, and MLK was given as an infimum involving the counting function n prime. And so an obvious first idea might be, well, let's try to lower bound n prime at d k to the gamma, where gamma is just slightly above the threshold, the Silverman exponent threshold. But that's not really a useful idea, because usually you can't give a non-trivial lower bound on this that works for most k, or at least it's kind of difficult to do that because you don't really know when this thing is zero, for which kind of gammas this is zero. So a much better idea is instead try to evaluate n prime a little bit above the threshold. So at delta to the d times a small fractional power of the discriminant. Because if you do that, then you're guaranteed to have already one small point, one generator of small height, and you can use this 1 point to construct many other generators. Okay, and we should assume here that L is at least d half. Okay, so once you know you got to prove this, everything becomes very, very easy, because to prove this lemma, you just have to combine 4 trivial observations. The first is just by definition of the delta invariant. We know that there is a generator alpha whose height is exactly delta k. The second trivial fact, if you have a non-zero rational number, then beta, then also alpha beta is a generator. Then you use the trivial upper bound for the height of a product, namely the product of the heights. And then you note that the number of non-zero rational numbers of height below t is of order t squared, at least if t is bigger than 1. And combining these 4 things, you get immediately the lemma. Okay, so this has a consequence. It tells us that MLK is pretty much exactly delta to the minus DL. So the lower bound comes when you consider the infimum that defines MLK over the range x smaller equals delta k. In this case, n prime at x is simply 0, and you get the infimum in this range is precisely delta to the minus DL. For the range x larger delta to the d, you use the previous observation, you do a quick computation, and you get the lower bound for MLK. And so you plug this in, and you found that FLD is just lim of d log delta k over L log dk, as k runs over all degree d fields. And now you just got to consider the worst possible situation, namely fields for which the Silverman exponent is sharp. And so here's a simple example, which I learned from the paper of Ruppert. If you want to construct a degree d field whose delta invariant is really small, you do the following. You pick 2 prime numbers, p and q, of similar size. You let alpha be p over q to the 1 over d. Then height of alpha is just q to the 1 over d. The degree of k is, of course, d. And p and q are both totally ramified in k. So pq to the d minus 1 divides dk. And this immediately gives you that the delta invariant is essentially at most dk to the 1 over 2d times d minus 1. Of course, you have infinitely many such fields for each d. And this gives you, if you plug it in this limit, gives you the upper bound of FLT. All right. So to end, let me mention that the key lemma of Ellenberg and Venkatesh has been refined in various ways. So the first important improvement, I believe, is due to Heath, Brown, and Pierce in 2017, where they allowed larger bounds on the prime ideal. And they were able to use this bigger bounds by also using additional tricks such as a Cauchy-Schwarz inequality and another trick as well. But anyhow, that gave them better upper bounds on the l-torsion part on average in case of imaginary quadratic fields. Another refinement in a somewhat different direction was given by Christopher Frey and myself. And in this refinement, we exploit the specific structure of the generator that appears in the proof of the lemma of Ellenberg and Venkatesh. And this works for arbitrary k. And more recently, Koymans and Thorne have combined both improvements to get the most refined version. And I should also say that this recent breakthrough of Chan and Koymans for 3 torsion in quadratic fields uses in an essential way that one can assume one can use larger prime ideals than in the original key lemma. And the way they can control the number of generators sufficiently well is by observing that they give rise to integral points in certain model curves and then using appropriate bounds. So I think it's fair to say that in the end, with additional refinements of the key lemma, Ellenberg's original strategy actually does work. All right, that's it. Thank you very much.